The average healthy adult on Earth can jump about 1.5 feet straight up, roughly 18 inches. That number depends on strength, age, and training, but it is a good working baseline. It assumes normal gravity, stable footing, and air thick enough to push against. What happens to that jump if we start moving outward through the solar system, from the places where gravity would pin you down the hardest, to the strange little worlds where a single leap might turn into a slow-motion glide? Let's begin where gravity is at its most unforgiving. On the Sun, if we imagine for a moment that we could stand on a magically indestructible platform at the photosphere, surface gravity is about 28 times stronger than Earth's. That means your weight increases by a factor of 28. Jump height scales inversely with surface gravity, so your 18-inch jump would shrink to less than an inch, about 0.6 inches. Not even enough to clear a thick textbook. Your muscles would fire normally. Your brain would send the same signal. But the Sun's enormous mass, which contains about 99.8% of all the mass in the solar system, bends space so steeply that upward motion becomes almost meaningless. Of course, at roughly 10,000 degrees Fahrenheit, you would vaporize long before worrying about leg day. But strictly from a physics standpoint, the Sun wins the contest for the smallest jump. Next comes Jupiter. At the level of its cloud tops, Jupiter's surface gravity is about 2.53 times Earth's. Despite being more than 300 times Earth's mass, its enormous size spreads that mass out over a radius more than 11 times wider than Earth's. If you could stand on a floating platform in its upper atmosphere, your 18-inch jump would shrink to about 7 inches. You would feel as if someone permanently strapped a very heavy backpack to your shoulders. The landing would not be graceful. The compression on your knees would be immediate. And that is before considering the radiation belts, which are intense enough to damage spacecraft electronics within hours. Moving slightly inward in gravity strength, we reach Neptune. Neptune's surface gravity is about 1.14 times Earth's. So your 18-inch jump becomes about 16 inches. You would feel heavier, but not crushed. Neptune is smaller than Jupiter, but it is denser than Saturn, which explains why it ranks higher in gravity. What would really get your attention are the winds, which can exceed 1,200 miles per hour, the fastest measured in the solar system. Gravity would not be your main concern. Staying upright might be. Saturn is interesting. Despite being 95 times Earth's mass, its surface gravity at the cloud tops is only about 1.07 times Earth's, so your 18-inch jump would drop to about 17 inches. In other words, nearly the same as here. Saturn's low density works in your favor. It is composed mostly of hydrogen and helium, and if you could find a stable surface at the cloud tops, movement would feel surprisingly normal. You would almost forget you are on a gas giant until you glance sideways and see the rings stretching tens of thousands of miles across the sky. Now we arrive back home to Earth, our middle reference point. Surface gravity is defined as 1 g, about 32 feet per second squared. Your jump is 18 inches. This value is not random. It reflects the balance between Earth's mass and its radius. Too much mass packed into a smaller planet and gravity rises dramatically. Too little mass spread over a large radius and gravity weakens. Earth sits in a narrow sweet spot that allows liquid water, a stable atmosphere, and bones that do not snap under their own weight. From here, gravity weakens. Venus has a surface gravity about 0.90 times Earth's. That means your 18-inch jump becomes roughly 20 inches. You would feel slightly lighter, slightly more springy. The difference is noticeable but subtle. Venus is nearly Earth's twin in size and composition, which is why the gravity difference is modest. Unfortunately, Venus has a surface temperature around 860 degrees Fahrenheit and atmospheric pressure equivalent to being nearly a mile underwater in Earth's oceans. So your improved vertical leap would be short-lived. Uranus comes next. Its surface gravity is about 0.89 g, very similar to Venus. Your jump would also reach about 20 inches. Uranus is tipped on its side by 98 degrees, leading to extreme seasons that last more than 20 Earth years each. From a gravity perspective, though, it would feel oddly familiar, at least for the brief second before you freeze in temperatures approaching minus 320 degrees Fahrenheit. Now we reach Mercury. Mercury's surface gravity is about 0.38 times Earth's. This is where things start to get fun. Your 18-inch jump becomes roughly 48 inches, almost 4 feet. You would launch upward in slow motion, hanging in the air nearly twice as long as you do on Earth. With almost no atmosphere, there is no drag to cushion your descent. Your motion becomes a clean ballistic arc, determined only by gravity and your initial push. On the sunlit side, surface temperatures reach about 800 degrees Fahrenheit. On the night side, they drop below minus 290 degrees. It is a dramatic place to practice your new superpower. Mars has almost the same surface gravity as Mercury, about 0.38 g. So your 18-inch jump becomes about 4 feet high here as well. The difference is Mars has a thin atmosphere, about 1% the density of Earth's. You would still move in that slow, bounding way we have seen in rover footage and astronaut simulations. Walking might naturally evolve into a series of long, loping strides because the energy cost per step changes under lower gravity. With Olympus Mons rising about 13 miles high, the tallest volcano in the solar system, you would have quite a backdrop for your extended airtime. Let's move to the moons. Io, one of Jupiter's moons, has surface gravity about 0.18 g. Your 18-inch Earth jump becomes nearly 8 feet high. You would rise in a graceful arc and take over 3 seconds to come back down. Io is the most volcanically active body in the solar system, constantly flexed by Jupiter's tidal forces. Its interior is kneaded by gravity itself. So while your jump would be impressive, the ground beneath you might not stay put for long. Our own moon has surface gravity of about 0.165 g. That gives you a jump height of roughly 9 feet. Apollo astronauts demonstrated this beautifully. They did not so much run as bounce. You would remain airborne for several seconds, long enough to start wondering whether you pushed off too hard. The fine lunar dust, sharp and abrasive, would cling to everything, and stopping your forward motion would require more control than you expect. Ganymede, the largest moon in the solar system, has gravity around 0.146 g. Your jump would approach 10 feet. Ganymede is even larger than Mercury in diameter, but because it is composed largely of ice, its mass and gravity are lower. It is also the only moon known to have a substantial magnetic field, generated by a liquid iron core deep beneath its frozen crust. Titan, Saturn's largest moon, has surface gravity about 0.14 g. That means your jump would exceed 10 feet, around 10.5 feet. Titan also has a thick nitrogen atmosphere, denser than Earth's. That dense air combined with low gravity creates an unusual situation. If you strapped wings to your arms, human-powered flight might actually be possible there, not because you are stronger, but because physics is working in your favor. Europa has gravity around 0.134 g. Your jump would reach nearly 11 feet. Europa's surface is a shell of ice, with a likely global ocean beneath containing more water than all of Earth's oceans combined. Callisto has gravity about 0.126 g, so your jump might reach around 11.5 feet. It is geologically quiet and heavily cratered, preserving billions of years of impact history. Triton has gravity around 0.079 g. Your 18-inch jump becomes roughly 19 feet. You would soar as high as a 2-story house and stay airborne for many seconds. Pluto has surface gravity about 0.063 g. Your jump would exceed 24 feet. You would float for nearly 10 seconds before gently returning to the nitrogen ice plains. Ceres has gravity around 0.029 g. Here, your jump would reach over 50 feet high. That is equivalent to leaping off a 5-story building and then slowly drifting back down. Enceladus has gravity about 0.011 g. Your jump would exceed 130 feet. You would remain airborne for close to half a minute. Finally, Phobos has gravity about 0.00058 g. Your theoretical jump would reach roughly 2,600 feet, about half a mile. In practice, you would likely exceed escape velocity and simply not come back down. On Phobos, jumping stops being exercise and becomes orbital mechanics. From less than an inch on the Sun to hundreds of feet on tiny moons, gravity shapes every movement. It determines how mountains rise, how atmospheres cling to planets, and whether a casual hop turns into a dangerous launch. Our 18-inch Earth jump turns out to be a quiet gift of living on a medium-sized world, orbiting a very ordinary star. If you enjoyed defying gravity across the solar system, go ahead and subscribe. We will keep both feet on the ground, at least for now.